Hi guys, I hope you're having a good day. I would like to talk to you a little bit about some removable discontinuities. Okay? Sometimes expressions might appear equivalent, but they may not be exactly. So how can you tell for sure? Well, let's start by looking at these first two problems. One of the ways you can tell for sure is by showing that they are equivalent. Okay? You can show that this problem is equivalent here by saying, well, there's nothing to factor, but here there's an x in the numerator, and both of these two terms are divisible by an x. If I divide each term by an x, I have x plus 2. If I then simplify my two x's, because they're both factors, I end up with 1 over x plus 2. Okay? Which is exactly my first function. So they are equivalent, right? Or they appear equivalent. So let's look at the tables. So if I do a new document that's a graph, no, I don't want to save my old one. In y sub 1, I want to have my fraction, so control divide, 1 over x plus 2. Okay? So there's that one. Yes? Then if I look at my second one, I want to tab to enter a new function. You can't see that, sorry. Control divide, give myself a fraction to work with, x over x plus 2x. Ooh, that's x squared, isn't it? X squared plus 2x. Look what happens when I enter it. Okay? So, graphically, do they look like the same graph? Do they look like the same function? Let's look at the table. Control T. So on this side of the page, we want to start at -2. So at -2, what's happening? They are both undefined. They both have an error. Okay? So undefined and undefined. Okay? At -1, they're both 1. At 0, At 0, my first function is 0.5, but my second function is undefined. At 1, my first function is 0.3 repeating, and my second function is 0.3 repeating. And at 2, my first function is 0.25, and so is my second function. So in what ways are the tables not equivalent? Well, in y sub 2, there is an error, or undefined, at x equals 0. Okay? So if we look at the graph of y sub 2, okay, let me see if I can show you how to do this real quick. Control T, so get the table to go away. I don't want number 1 to be graphed. And there's a way to make that happen. I just don't know yet. I apologize. So we're just going to delete this one. Maybe. Not like that. Little cursor. Okay, so we're just going to delete that one. Okay, so this is all I have right here. Okay, so if I'm sketching the graph here, I have an asymptote at -2, and it does this, and it does that. Correct? How many vertical asymptotes does it have? Well, it has 1. Does that match the information in this table, according to y sub 2? No, it doesn't. Okay? No, there are 2 undefineds in the table. Okay? There's only 1 asymptote, but 2 undefineds, which would imply that we would have 2 asymptotes, right? Okay? So look over here at this one. Find the vertical asymptote of this function by setting the denominator equal to 0, just like we did yesterday. Okay? So 2x minus 6 equals 0. If I add 6 to both sides, I get 2x equals 6. So x equals 3. So I know I should have an asymptote at 3, correct? So when I look at my table, oh, I gotta put this in real quick. Let's tab to get the equation. And the one I have is in y sub 2. So let's do x squared, where is it? x squared minus 3x over 2x minus 6. Well, that's odd. Control T gives me my table for this function, and if x is at 0, y is at 0. If x is at 1, I have 0.5. If x is at 2, I have a 1. When x is 3, I have an undefined. And when x is 4, I have 2. So it seems like from this table I should have an asymptote at 3. But we already know what the graph looks like. First of all, does the table support the location of the asymptote? Yes, it does, because it's undefined. Okay? But if we sketch the graph, this strange thing happens. It looks like that. So why do you think I think it's strange? Why does this ask what's strange about the graph? Well, it's linear. That's strange. These are rational functions. These should look more like something like this. Okay? But this one is linear. So the strange thing about this that I can't show you on these calculators is that there's also something, like I said, there's also something else that's strange on this graph. This calculator doesn't show it because it's too good. There's too many pixels on the screen. We don't have room to show it to, but actually what's happening, if you look right here at 3, there's actually no value there. Okay? Just like according to the table there shouldn't be anything there, there's actually something right here like that. So this is the day that a lot of you are going to enjoy, because not only we're talking about asymptotes, but we're talking about holes. Can you handle talking about both of those in the same day? I hope so. Mrs. Morris needs your help doing that. Okay? So usually values of x that make the denominator equal 0 will create a vertical asymptote, unless that value also makes the numerator equal to 0. Okay? If it also makes the numerator equals to 0, this doesn't create an asymptote. It creates a removable discontinuity. Okay? So normally we set the denominator equal to 0 to find the asymptotes. Well, this time we've got to set the denominator equal to 0, but we also have to make sure both numerator and denominator are factored, because when something occurs in the numerator and in the denominator, that's going to create a hole in the graph, a removable discontinuity. Any other part of the denominator that's not simplified out, that doesn't simplify to 1, this is still going to create a vertical asymptote. Okay? So here's some rules for you. If you plug in an x value and get a number divided by 0, then your graph will have a vertical asymptote. Okay? But if you plug in an x value and get 0 divided by 0, you're going to have your graph is going to have a removable discontinuity. But you can't just rely on the table, because the table is going to say error or undefined no matter what. So to make sure, you have to factor. Okay? So I'm going to do one of these for you. I'll do number 1 for you, and you're going to do the rest. Okay? So if we factor the numerator here, we're going to get x plus 2 and x plus 4. If we factor the denominator, we're going to get x plus 2 and x minus 3. So in this case, these two would cancel out. So that's going to create a removable discontinuity. Now, where is it going to be a removable discontinuity? Well, I still have to follow the other rules. I have to set it equal to 0. So x plus 2 equals 0 will give me an x value at -2. So my removable discontinuity, or my hole, is going to be at x equals -2. The other value in the denominator will give me my vertical asymptote. So once again, I still have to set it equal to 0 and solve. but that's going to give me my vertical asymptote, x equals 3. Now, horizontal asymptotes from yesterday, I think. You may have to get out your reminder page, the reminder notes that we talked about, finding horizontal asymptotes. But hopefully you'll remember, if my degrees are the same, then I look at my leading coefficients at the very front. Well, this is 1 over 1, so this is going to tell me my horizontal asymptote, and I'm going to have a horizontal asymptote at y equals 1. Okay? Any questions about that? All right. The next worksheet you have is called the Giant Inmate. Okay. Late one night, from atop a 35-foot tower, prison guard uses a lantern, because that's what prison guards use nowadays, is lanterns, to catch an inmate trying to escape. The guard easily spots him because the inmate is 7 feet tall, as are most prisoners. Okay. In fact, the inmate only makes it 12 feet from the prison before the guard yells for him to freeze. Then the guard proceeds to climb down the tower. As he descends with his lantern, the guard notices that the frozen inmate's shadow gets longer and longer. So we're going to let x equals the height of the guard as he climbs down, so here. And we're going to let y equal the length of the shadow. Okay? So let's use some similar triangles to figure in the figure to set up and solve a proportion to find the length of the inmate's shadow when the guard was at the top of the tower. So when the guard is at the top of the tower, we have a 35. X is going to be 35. So the height of the guard over the length of the shadow. Is that what I want? How about the height of the guard over the height of the inmate? That would probably be better. Okay, height of the guard over the height of the inmate. So we're doing tall parts of the triangles. So then we need long parts of the triangles. Well, the long part of the big triangle is actually 12 plus y, and then the short part, or the long part of the short triangle, the small triangle, is y. Okay, so to solve this, we have to cross multiply. We have two fractions set equal to each other. We cross multiply. We multiply there, and we get 35y. We multiply here and we get 7 times 12 plus y. Okay? If we distribute here and here, we get 35y equals 84 plus 7y. Well, to solve for y, I just subtract 7y from both sides. So 28y equals 84, and then divide everything by 28. Y equals 3. So at the time that the guard was at the top of the tower, the inmate's shadow was 3 feet long. Okay? So what I want you to do now is I want you to put this into a table, this equation right here, because it says a function can be used to show this relationship. Okay? So I want you to put this into your table. I want you to plot those points onto this graph, and I want you to find the asymptotes, both vertical and horizontal, and explain what they mean in this problem situation. Okay? The last worksheet I gave you, please make sure you do this before you leave. You can do the last one later, but you got to get the table before you leave. You can always plot the graph later. The last one I have for you is this one, this worksheet called Graphing Practice. Okay? I want to fill in the top notes for you, so you have those, and then I'll let you do the rest of them. It's just some practice on finding asymptotes. Okay? So number one, you have to locate the vertical asymptotes. How do we locate vertical asymptotes? Well, we set the denominator equal to 0. Okay? Determine the horizontal asymptotes. Well, to find the horizontal asymptotes, we compare degrees of the numerator and denominator. Refer back to that other page of notes we talked about finding horizontal asymptotes if you need to. Determine points of discontinuity. Okay? When we factor the denominator and we factor the numerator in that case and find a common factor in both numerator and denominator, that's going to be your point of discontinuity, and you've got to set that equal to 0 to find the points of discontinuity. Okay? Or the removable discontinuity, I think is what we called it on the other sheet. Draw the asymptotes with dotted lines, make a table of important values, and then plot the points to sketch the graph. Okay? This is what I will check on Monday. I hope you have a great weekend. I will see you soon.